My name is Jianying He. I'm from Norwegian University of Science and Technology. Usually in this meeting, I talk about like a hydrogen embrittlement or something, but today I decided to talk a little bit different topic, how we can use the phase scale to enable the new fracture mode that's lower the interface adhesion. And you probably know that Norway is really in this northwest corner of the whole Europe. And our university located here in the middle part of Norway, and you can see it's around 600 kilometers from the Arctic Circle. So in the wintertime, we have a lot of icing issues. Then the ice became a problem in the daily life and in the industry. That's how to lower the ice adhesion and to remove the ice is a question here, and it's also the research purpose we have today. So I will follow this outline. First, the definition of the ice phobicity, and then how we can use the fracture mechanics-based concept to design the surface with lower ice adhesion. Then it's the phase scale enabled low ice adhesion and other biomimetic ice-phobic surfaces we have. Before we talk about the icing problem, this is probably the concept that many people know, that wettability and superhydrophobicity. Wettability concept is pretty simple. We have here the contact angle, describe how the force balance at this three-phase contact region from the vapor, solid, and liquid. And then we use the contact angle to characterize the surface wettability. If it's below 90 degrees, it's hydrophilic. And if it's above 120 degrees, it's hydrophobic. In the middle, it's mixed white, right? And then if we can further increase the contact angle to over 150 degrees, then we will have the superhydrophobicity, which means that the surface repels water all the time. And if we want to realize this superhydrophobicity, only the surface energy is not enough. We further need some surface structuring. That's why the research society mimic those like the biosurfaces, for example, lotus leaf or the butterfly wing, or some other type of those biosurfaces to design those superhydrophobic surface. And in long time, that also the icing people believed that this superhydrophobicity also hold the key for the ice-phobic surface. Because if we don't have any water stay on the surface, of course, we don't have resource to form ice. So then in long time that people focus mainly on designing those superhydrophobic surface and for the application of the anti-icing. The problem is that later people found out, even in the high humid environment, that means with the high vapor pressure, then actually the droplet became super small and it will enter into those pockets of this surface structure necessary for superhydrophobic surface. And if those droplets freeze and then connect with each other, then we form actually this big ice on the surface structuring. And this will be even more difficult to remove. That means superhydrophobicity doesn't mean ice phobicity. We need a new strategy for the surface to repel the ice. How to do that? Traditionally, we have active de-icing method. That means we need to pump the energy into the system to remove those ice. And that could be like the mechanical force, could be the electrical heating process to melt the ice and to remove, or could be the chemical method. Like in Norway, often in winter, we use a lot of salt to melt the ice on the road. However, all those need a large amount of the energy input and probably also need very heavy labor work to remove. So can we find the strategy which we don't need to pump so much energy and to have the passive anti-icing behavior? And the answer is yes, possible. And there are three steps for those passive anti-icing strategy. First, of course, if we have a surface never adhere with any water, then we don't have the resource for the ice. And that's probably the superhydrophobic surface. But we have confirmed that at a low temperature and high humidity, it doesn't work for a long time. Second step is that if we can delay this droplet freezing time to form those frost, then we have time to remove water droplet coming onto the surface. And think about that in Norway, the winter can be up to 7 to 8 months. So this delaying the droplet freezing is also very temporary strategy. Then we have to probably live with ice. But if we can design a surface which has the lowest ice adhesion, that means by natural wind or by the own weight of the ice, then it can easily remove from the surface. And this is probably the most practical solution for the anti-icing application. Yeah, so talk about lowering the ice adhesion. Then similar as the wettability, we have contact angle to quantify the wettability. For the ice phobicity, can we find a similar parameter to describe that? Then it's very naturally we are thinking about the different range of the ice adhesion strength. So talking a little bit more about that, the ice itself has the tensile stress up to 3 megapascal. While the typical metallic surface, without any surface structuring, it has the ice adhesion larger than 600 kilopascal. Well, that composite surface without other surface treatment with those low surface energy functional group, it's around 200 kilopascal. So if we want to further reduce ice adhesion, then we need to do the surface treatment, either some kind of like a graft the functional groups, or probably do some surface structuring, or even like tune the surface other properties. Then our group defined this ice-phobic surface should have the value below 100 kilopascal and even low ice adhesion surface below 60 kilopascal. And around 5 years ago, we even have make the surface with super low ice adhesion, and that's below 10 kilopascal. The physical meaning of this silias is quite simple. If we have 1 cubic meter ice attached to the surface, and to destroy this interface by its own weight, then it needs this 10 kilopascal. So the physical meaning is simple. Then we design the surface, try to meet this requirement. How to do that? And if we see this model, how the ice attach onto a surface, and we have a shear stress to remove it, and it's opposite to any other fracture mechanics research that try to prevent the crack. And here that we are thinking we can promote the cracking at the interface. So the shear stress at the interface can be described like here. And many other research try to focus on reducing the Young's modulus and the surface energy on the top here. Then we can reduce the shear strength. But since we are talking about the fracture in the whole conference, so is it possible to find a way that we can maximize the interface crack length so that we can also minimize the shear stress? To realize that, what do we need here? Then we need to create this macro scale cracks at the interface. And to realize that, we have to increase the deformation incompatibility between the ice and this substrate. And how to realize that, then we can think about a kind of like the soft substrate with the subsurface structures. So you can imagine that when I push the ice on the top, I create multiple this stress concentration sets at the interface. And every this concentration sets can serve as a crack initiator. And if all of them initial cracks at the same time, so then we maximize the total crack length, and we can realize the super low ice adhesion. This is one of the examples we have. It's a sandwich like a PDMS sponge. So top and bottom layer are smooth PDMS layer, while middle is a porous layer. And in the illustration drawing, it's ordered structure, but in the real material, it's very disordered, this porous structure. We use the sugar template to prepare those sponge. And then we found out that the ice adhesion strength is very low, around 1 kilopascal. And even with the cyclic icing, de-icing process, it kept the very low ice adhesion around 1 kilopascal. So it's not only silias, it's very durable silias surface we developed. Then we are thinking that if we can use the other way to create a new fracture mode to further reduce the ice adhesion. So here is the Norwegian salmon. it's not only very nice meat, it also can serve as our experimental material. Since the salmon usually is huge, so we have a large area of those fish scale. And then we are thinking that if we can use the anisotropy of those fish scale to realize the new deformation mode or fracture mode, how to understand that? That if we attach ice cube on the surface, and you can imagine we can share it in different directions. It could be 0 degree along this scale growth direction, or 90 degree, or even 180 degree against the fish scale growth direction. So then we can realize different this fracture mode. If along or perpendicular to the growth direction, we will have the concurrent rupture. All the contact point between the ice and the fish scale will fracture at the same time. But if we share it along this 180 degree against the scale, then we could have this sequential rupture that the contact point at the interface will fracture one by one. So that means this is sequential rupture. So this is the design concept. And then we easily realize that the student just bought this big fish from the market, and they eat up all the meat and keep the scale, the skin, for our experiment. And they freeze ice on the scales. And then if we share the scales, we found such a behavior. An initial part and deformation start. Then it's a really long, this like a deformation process. And when we observe that, it includes this scale separation and also peeling off process. And it will realize this sequential rupture. That's why they have really this long kind of elongation process. I have a video to show how this sequential rupture happens at the interface. If we push this cube with the ice inside, and you can see that those scale, they will actually rupture one by one, and they have the large deformation and then the separation of the ice from the substrate. And interestingly, the process is also connected with the fish scale size, because the different part of the scale has different size of the individual those scale. And then we found out that this S adhesion reduction is connected with the fish scale size. And our molecular dynamic simulation, just with those graphene plate, mimic the fish scale and will demonstrate this size-dependent ice adhesion behavior on the fish scale. So if we compare the ice adhesion strength with other material, we can see that the fish scale has quite like the nice behavior in terms of the strength and the ice adhesion behavior. So it has much higher elastic modulus than the plastic and the rubbers. Although the elastic modulus is lower than the metal and ceramic, but the ice adhesion is almost like 3 times lower than metal and ceramic. So it can be a very good candidate, material candidate for the low ice adhesion material. And of course, that we also work on other type of those biomimetic anti-icing surfaces. These are 4 examples, like this ionic gel surface to mimic how the ion mitigation through the human skins. And they also show very low ice adhesion. And also this epidermal gland inspired surface, which contains those lubricant inside the material, can well reduce the ice adhesion. Or like those onion-like behavior, the onion-like surface, which has the cell and also this porous structure. And it further confirms our macro scale crack initiator mechanism to lower the ice adhesion. And of course, that we combine different those functions like the self-healing or the transparent surfaces, which can be used in the outdoor application, like those monitoring video camera and so on. Yeah, so come to the conclusion that those biomimetic surface can significantly lower the ice adhesion, and especially this fish scale enabled this new fracture mode, sequential rupture, to lower the excitation, like such a process. Then we are very interested in other type of the phase scale or the biomimetic surfaces. If you have any good idea for collaboration, you're always welcome to talk with us. Then we are also interested in using, for example, the 3D printing or like those laser-based method to design those artificial phase scale samples and to further lower the excitation. And here that if you have a good idea, also welcome for any collaboration. Yeah, with a big salmon on the ice. Thank you for your attention.